Hi, this is Mr. Mack. Now, in this video, I'd like to talk to you about the formal definition of limits. Now, this definition is attributed to a mathematician by the name of Cauchy. And what we're going to do is we're going to define the limit as x approaches a of f of x. Now, we say the limit as x approaches a of f of x. Oh, first of all, let's take care of some details here. Let's let f of x be defined on an open interval about a, except possibly at a itself. This is kind of stilted. Let's see if I can explain this. What we're saying is that there is some interval of numbers. It's open at the end, so open circles. And it contains a, and the function f is defined on all the values in this interval, except it might not be defined at a itself. But remember, we're not really going to look at f of a, although yeah, one of the techniques we showed you was direct substitution. But the real concept here, we're trying to do a formal definition, is what are we squeezing in on as x gets closer and closer to a. So we don't really need to look there, although that's a very useful technique when we're evaluating limits of continuous functions. So let f be a function defined on an open interval that contains a, or about a, except possibly at a itself. Now we say the limit as x approaches a of f of x equals L if for every, let's use that universal quantifier symbol, for every, upside down a, for every epsilon greater than 0, there exists a delta greater than 0 such that whenever the absolute value, 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Obviously, right? Well, let's talk about this a little bit. Okay, the first thing that you need to see is what we really mean when we say the absolute value of x minus a is less than delta. So let's come out here and do a number line, and here's 0. Somewhere over here we're going to put a. Now, the absolute value of x minus a is less than delta. It's an absolute value inequality. Now, this was covered in Algebra 2, but I find that a lot of times Algebra 2 students don't remember it at this, or calculus students don't remember it at this point, number one. Number two, even at the time, they didn't really see it as that important. So we need to go back and take a look at this again. Now, if you look at this expression right here, one way of saying this is x is all numbers less than delta away from a. See, in other words, this represents an open interval that has a as its center and delta as its radius. So if we were to go delta units this way and delta units this way, and then do open parentheses to show an open interval there, all of these numbers in this interval would satisfy this absolute value inequality. Now, when you look at this absolute value inequality, that's what your mind has to see. A is the center, delta is the radius. So we have an open interval, center at A, radius of delta. Okay. Now, notice here we also have 0 is less than, so we're actually excluding a itself in our formal definition. In other words, we're going to look at the numbers less than a and greater than a as we come towards a, but we're not going to look at a itself. That's why this 0 is less than absolute value x minus a is in there as well. Now, this is an absolute value inequality as well. Absolute value f of x minus L is less than epsilon. Now, let's just draw a y-axis right here, and let's make this the L right there. And let's imagine we have some function f like this. We'll call that f of x. Now, notice that if we were to take all of these values in the delta interval around a and map them using f to the y-axis, we would get this open interval here. Now, what we're going to do, okay, and so this would be, let's just start out by saying this would be the epsilon radius around L for another open interval. Now, what we're doing here is we're saying in this definition, this formal definition of limits, is that this is going to be a bit like an argument. Somebody and I are going to have an argument about whether or not a function, this function has a limit, or this function's limit is L, let's say, at A. Okay, and maybe I will claim, yes, L is the limit, and then you will say, okay, then let me give you an epsilon, because it says, for every epsilon greater than 0. So you get to give me the epsilon, and then I get to pick the delta. See, for every epsilon greater than 0, there exists a delta greater than 0. We're arguing about whether or not the limit exists, and so you say, or I say it's L, and you say, well, I'm not sure I believe it. And so I say, okay, you can give me any positive epsilon you want, and then I get to choose a delta. Now, notice, if you choose a very large epsilon, it'd be very easy for me to find a delta that would map everything in there. So what you're going to do is you're going to choose a smaller and smaller epsilon that's greater than 0. And see, that's where this idea of squeezing in on it occurs. Then I will pick a delta greater than 0 so that all of the values in my delta interval around A will map inside your epsilon interval around L. And if I can convince you that I can always do that, then I've successfully argued that this function's limit at A is L. And that's the formal definition. Now, guys, some students have wandered in here and want to talk to me, so I'm going to pause this. I am back. Now, let's play with this just a little bit. Let's imagine that we have a function that does something like this. Let's see, this is L here, and this is A, and then it, well, it's got to be an open circle there. Then it does something like this. Now, let's say I'd like to claim that for this f of x, that the limit is L. Claim the limit as x approaches A of f of x equals L. Now, it says for every epsilon greater than 0, there exists a delta greater than 0. So let's say you pick your epsilon so that it is this high here. Now what I've got to do is I've got to find a delta that we could put around A so that everything in that delta interval around A will map into the epsilon interval around L. Now notice, since we've got this discontinuity here, and this is an open interval, there has to be some points over to the right of A. Now if we take this one up here and then map it across, if you've just made epsilon smaller than the distance between this closed circle and this open circle, this is not going to map into, or not all of the values will map into your epsilon interval, and you've successfully shown that L is not the limit for f of x as x approaches A in this particular case. Now, I'm going to challenge you to take a look at the definitions for left-hand and right-hand intervals, limits, and then also for infinite limits, and see if you can't reconcile those in your mind. That's a good exercise for you. And that concludes the concepts on 2.4.